One of the most important theoretical probability distributions that we will use in this course, or virtually any other statistical course, is the normal distribution. The normal distribution was developed by a mathematician called Gauss, so it's sometimes called the Gaussian distribution, and it's a distribution that is generated purely by chance. And the distribution looks like this. It's a symmetrical distribution, and the height of this thing represents probabilities, and we can use this to evaluate all sorts of very important things. Now, what we actually also have is we have a mathematical function for this. Now, this is the mathematical function for the normal distribution. Now, you can see there's the value of x, and that's fx. That's the dependent variable. These other things in here are actually numbers. Pi is the number pi, 3.14, whatever it is, or 22.17. Sigma is the standard deviation of this distribution, and mu is the mean of this distribution. Okay. Now, what we are often trying to do is, if we find that a real-world situation, a real-world financial situation can be modelled using the normal distribution, then we can make very definitive probability statements about what's likely to happen in the future using this theoretical distribution. Now, if we want to go through and look at this example here, example 5c, what I've got here, I've got, that's the values of x, goes from -3 to +3. Now, these things here I've worked out using this formula here, and that's that formula, and the spreadsheet works all this out. But at the moment, I've got mu of, I don't have mu or sigma. So let me make mu, which is the mean, 0, and let's make sigma equal to 1. Now, if I do that, you can see what I've got. That's my normal distribution. Now, if I make sigma equal to 0.5, then it's the same it's a normal distribution still, but the standard deviation is much smaller, so you would expect this thing to become thinner and pointier, and this thing here will intercept much higher up. So if I hit enter, it goes up here. Instead of crossing at 0.4, it now crosses at 0.8, and of course that makes sense because the area under any probability must always be 1. Okay. If I make it equal to 2, of course it makes it much fatter. If I make it back to 1, but if I start changing mu, that is the mean, then of course if I make that 1, then of course I'm going to move this to the right. Okay. Now these things are all normal distributions. If we are trying to use this distribution to make probability statements about the future, what we'd actually have to do is we'd have to work out the probability by working out the areas under the curves. Now the area under a curve, as you remember from your calculus, involves you finding the integral of this. Okay, so you'd have to use integral calculus to find the area under the curve. That would be tough. Fortunately for us, Gauss worked out the areas under many different normal distributions, but then he got a simple one, which is where sigma is 1 and mu is 0. If sigma is 1 and mu is 0, this is called a standard normal curve. All of the ones I've got before are the normal distributions, but if sigma is 1 and this is 0, then that's called the standard normal curve, and it looks like that. And then what he did is he worked out the area under it for a whole range of different z values, these things here, and put them into a table. So all you guys have to do is to make sure that you can use the table properly, and you can confirm that using the functions in Excel, which do the same thing, and you're bound to be asked in your final exam to look up these tables.